glad to see you all here. On behalf of the Global Outreach and Extending Education Office at ASU and the Fulton School of Engineering, welcome to the Introduction to Electronical Concept in Semiconductor Packaging Microbatches. This course is part of the Scalable Micro-Credential portfolio, which offers a cutting-edge approach to learning, designed to align with your skill with the dynamic needs of today's workforce. Each micro-credential is taught by ASU faculty and industry experts, providing flexible, targeted learning in emerging technologies, including smart manufacturing, robotics, and automations. This program is the second batch of the Semiconductor Packaging Fundamental Concept and the Driver Badges series. A special welcome to the industry professions, ASU's engineering student, and the EASY participant of faculty programs, many of who joined us for the first micro batch. Thank you for continuing with this program with us. As some of you may know, today's section will use the Canvas shell for the group activities, discussion, and submission. So please make sure that you're able to log into the Canvas shell. We have sent out the invitation multiple times. If you're still having issue accessing to the Canvas shell, please share your email with me in the chat so we can resolve it. A quick introduction. My name is Leaky Lee. I will be assisting you, supporting you with any administrative needs. Please don't hesitate to reach out if you have any question or related to Canvas or all those non-content topics. For the content-related questions, we will have time for Q&A during the sections, and you are welcome to email to the instructor as well for additional question after forward. Just like the last micro batch, we have two instructors for this batch. Professor Terry Alford and Professor David Seattle, both professors in the School for Engineering of Matters, Transfer, and Engineering, for energies. They will guide you through the course for the materials. With that, I will hand it over to Professor Alford. The floor is yours.
Thank you. Thank you very much. And good morning to some and good evening to others. I look forward to working with you all. Please feel free to ask questions if need be. And if we get to a point where there's too many questions, I'll say, okay, we'll move on and give you opportunity during the break to ask questions. All right, so we're going to start off with a little review from last week, just to warm us up. And okay, so hopefully you can see my screen. All right, so it's Introduction to Semiconductor Packaging, just a review. And so let's go. Excuse me, why is that?
You want me to pull out the pods, Bradley? Okay, you have.
Yes, here we have the first one.
Yes.
What are the functions of the semiconductor package? Power delivery, cooling, signal routing, interconnection, all of these, none of these. So we have the poll. So you can answer these questions. I gotta get my notes so that I can take. Okay, we're gonna. Okay. 30 more seconds. Give you time to become familiar with polls for those who are new. Okay, 5 more seconds. Okay. And if we go, the actual answer, oops, why is that? Correct, all of these, great. Okay, let's go to the next one. When designing a package for scaling with Moore's law, one can design for lower costs or ISO features only, higher compute at ISO die size only, none of these, both of these. Okay. Okay, we're going to take 25 more seconds. Ten more seconds. Okay. And we actually can design for both of these. We're not limited. Yes, we can go to lower costs with the same features, or we could try to get higher computing with the same die size. Both of these approaches are valid when trying to scale for Moore's law. Okay. And what is the function of the underfield? Does it provide electrical stability, mechanical stability, thermal stability? Okay, we can go ahead and launch the poll for this one. All right, we're only going to take 30 seconds for this poll. So I will give you the 15-minute mark is now. Okay, the function of the underfill is to provide mechanical stability. Typically, this is when we're going to put the epoxy under the solder bumps or C4 solder bumps and let it flow, heat it up, it flows under, and then when it cures, it becomes stiffer and provides mechanical support. Okay, thank you. Okay. Now this one, we're looking at decoupling the silicon chip floor plan helps blank and blank the complexity for allowing reuse of for multiple products. And we'll give you a little bit longer with this one. We'll go back to the minute. Okay, we're at 35, we have 20, excuse me, 20 more seconds. 15 seconds. Okay. And this one, a little, remember the decoupling the silicon chip floor plan allows, helps to, uh, helps for, I should say, size and design complexity, and you get to reuse the design board. So you could have multiple products on the same design board, but be different technologies, okay? So again, it helps, by decoupling it, helps with size and design complexity, but it also allows you to reuse that same board for multiple products. And then I think this is the final one. This is the tough one. Okay. Define the acronyms. Oh, make sure, now look down at the bottom. You have to get the QR code to participate. So we'll go a little longer here. So make sure you get the QR code to participate. And then from once you get the QR code, you can go to the pull down for each acronym. Okay, I see we have some people participating. Great. Okay, we'll take 30 more seconds. Or maybe we'll go, see people starting to really chime in right now. Okay. 20 more seconds to try to get. Ten seconds and okay. So let's fix it. Okay. So we'll look at the answers. Dual inline memory module, PCL, tightly coupled memory, solid state drive, serial advanced technology attachment, optical disk drive. So let's go back. Okay. One, small circuit board containing multiple RAM chips. The PCL, okay, high-speed interconnect to the motherboard. Yeah, and it usually this is sort of a direct link, okay, to the most important components like the memory, the accelerator, graphics. Okay. Oops. TCM, memory offers minimum delay. Okay. 5 transport protocol and ODD, optical laser write and read. Okay, and then this should be, oh, we're gonna, this one, hopefully you remember, because we're gonna bring this, we're gonna actually utilize this tonight as well. For decoupling capacitors with N number with the same value. So we have N number of capacitors, they have the same capacitance, and they're in shunt. We have inductors, which also number is N with the same level of inductance. And we have resistors N number with the same value of R. And the equivalent circuit has values of inductance, resistance, and capacitance, respectively, as A, B, C, or D. So we're going to put those inductors, resistors, and capacitors. They're going to be in parallel here, but they're going to be in our circuit. Oops. But in our circuit, they're going to be in shunt. Okay. Uh-oh. Not good. Okay. We're going to take 15 more seconds. Well, okay, there we go. Okay. Yes. We lowered the total inductance by L over N, the resistance by R over N. However, the capacitance is accumulative, okay? It reduces the parasitic inductance and parasitic resistance. Unfortunately, it will increase the effective capacitance. And so we will utilize this later on this evening. All right. Any questions that I may ask before we continue? Okay. All righty. Next one.
Participant raised the hand. You want him to unmute himself and speak out the questions?
Yes.
Okay.
Hello?
Yes.
Oh,
Hi. So I didn't get the answer for the last question.
Okay. Okay. And do you see it now?
Yeah.
Now it's okay.
Okay. Hello? Are we good?
Yeah.
Okay. Stop sharing. Do. What? Screen two. Okay. All right. So I don't know where that is, but okay. Okay, so for some reason it's over there. Okay, so we're going to, um, do you see the basic elements of the circuits part one?
yes.
Okay, so off we go. Why is it not changing? Okay. So we're going to talk about um, electrical time domain. Okay. So with this, a lot of people get a little, I would say, nervous if they haven't seen time domain, frequency domain. And so simple analogy, I mean, way to look at it. Here, we're going to talk about baseball to help us understand this. So we're going to talk about time domain and frequency domain, but make it in reference. Start off with a little bit of baseball. So let's find, okay. All right. So he has a glove. And the gloves are meant to catch the ball. The ball was coming at him at 104 miles per hour. He had a glove. The whole premise of the glove is to catch the ball. However, if we look here, notice there are two types of glove. There's a catcher's mitt that the catchers are using. These two young ladies are playing the position of catcher, and they have a glove or catcher's mitt. Here we have an infielder catching a ground ball, outfielder catching a ball that's about to be a home run. Okay, both of them are gloves. However, they serve two different functions. But they still catch the ball. And that's what we want to get to when we talk about time domain analysis and frequency domain analysis. The time domain, we're going to analyze the signals as they change over time by the name, time domain. We're going to look at the signals of the system as well as its behavior as it evolves at certain moments, or we should say certain moments in time, okay? And in both, we'll use plots to measure how these values vary, whether it be frequency or time. If we go over to frequency domain, okay, we're going to analyze the signals as a function of frequency. Here, we'll employ some signal processing techniques to actually make a connection between time and frequency domain. A lot of times, when we're over here in frequency domain, we're going to look at an instance in time. Okay. Now, why do we have both? We can utilize both. Doesn't matter which one you choose. However, over time, typically frequency domain makes the math easier, but you can go back and forth. It does not matter. Okay. So just remember, it's just like the glove. They're both are going to do the same thing, but just differently. Okay. So when we look at time, or when we look at the analysis of a signal, I can look at it in time domain or frequency domain. So I have this what some may say, a very sophisticated signal in the blue, and I want to analyze it. I can analyze it as in trigonometric functions. I can break it down in trigonometric functions. One where it'll be a function of the frequency, and the other, I can have it as a function of time. Both will describe the signal, okay? But they're just describing it in different domains. One is going to be a function of time. The other one is going to be a function of frequency. Again, but we can get the same amount of information. Okay, so again, we're going to take this very complex signal, decompose it into a series of trigonometric exponential functions, and then describe it either in a time domain or in the frequency domain. Now, when we talk about the frequency domain, you know, we're very comfortable with time, okay? But frequency is a little different. We have some variables that we have to make sure we clearly understand. Okay, so let's take a moment for inquiry. So what I would like for you to do is define these variables and then give the units for those variables. Okay, so let's take a moment to do that. Great. And absolutely correct, man. Yeah. Perfect. All right. So let's look. It's over there. Okay. So wavelength, the speed of light divided by frequency equals the speed of light times the period. Angular frequency is 2 pi times the frequency. And if I look at period, it's 1 over frequency. Let's look at the units. Well, lambda, wavelength, is in meters. Speed of light, meters per second. Frequency is 1 over seconds. Speed of, that's CT, so that's meters per second times seconds. Let's go to angular frequency, that's radians per second, okay? And 1 over second, or actually should be radians per second, okay? Gotta get that radians per second. Okay, and period is seconds, because it's 1 over frequency. 1 over 1, okay? What's that frequency? That didn't change, didn't correct. All right. So make sure this one should be radians per second and 1 over seconds to give you seconds. Okay. Now, how do we go from time domain to frequency domain? It's typically done by Fourier transformation. We won't get hung up, but what I want you to grasp is that there is a mathematical means by which we can just go from one domain to the other seamlessly. Okay. And this approach is utilizing Fourier transformation. Okay. We can just go back. Sometimes people use the term forward transformation, going from time to frequency. Backwards transformation, we're going from frequency to time. Doesn't matter which way you're going, is where we can describe this signal in terms of frequency or time. So just be comfortable knowing that, hey, if people talk about time domain, you know it's going to be a function of time. If it's frequency domain, it's going to be a function of frequency. Okay? Either way is okay. All right? Now, again, just look, if we look at the function, not a whole lot to it. It's just that we have to be aware that this J, okay, that we have in both equations, that J is just the imaginary number, square root of -1, okay? So that's what that is. So other than that, everything else is the same. So we have our angular frequency, we have time, they're interrelated. You have your function of time, and we can convert that or transform that into a frequency function. Or we can have a frequency function, and we have our angular frequency and time, and we can convert that into a time function. Okay? So there's software that can do it, you know, don't worry about having to do it, but just be aware that we can go each way based on this Fourier transformation. Okay. Now, what does it do? We start off with this it's a very simple square function, okay, such that the negative 1/2 of our period to the positive 1/2 period, the amplitude of this function is A. So for one period, the amplitude is A. Outside of this period, the function goes to 0. Prior to this period, half period, the function is 0. Okay, so as we have here, this function of t has amplitude A greater than the absolute value greater than less than equal to t 1/2, less than t 1/2, the absolute value. Anything beyond that, it's going to have a value of 0. Okay. Now, with our Fourier transformation, we can transform this function into the frequency domain. Okay, not so bad. Well, the nice thing about it, we can actually, describe this function very well in the time, obviously very well in the time domain, as well as in the frequency domain. And we can actually go back if need be. Okay, so if you look here, the Fourier transformation is an infinite frequency extension, meaning the frequency component extends over a much larger range. Okay? So it gives you ability to actually make the transformation finer. Okay? And that sort of makes it easy with the math. You have this sort of this, you can take this square function and convert it into this angular frequency function. Yeah. Then I could take this angular frequency function, transform it back, and it'll give me the square wave. Okay. So again, we just take complicated functions and convert them into trigonometric and exponential functions that can go back and forth. Okay. Not so bad. Okay. And why is it important? Well, when we start talking about some of the signals, we're going to talk about signal integrity later on. If I have this nice, clean function, square function, I can describe it by a nice, clean angular frequency function. If the periodicity changes, no problem. It converts again to a very clean angular function, right? So that's what we want. We want to a very clean function as the signal propagates. We want to stay rich, have the same information. Okay? But life is not always fair to us because sometimes we can get degradation over the frequency. Okay. And if we look here, where I really had this nice square wave, now it doesn't it transform, or as it propagate, I get some degradation, and I don't get the nice symmetrical geometric function. I get some degradation. Okay, and even when I go to higher, I go to a different frequency, I can get degradation in the quality of the frequency. Okay, or determining the frequency, as well as I get degradation in the amplitude. So when we talk about signal integrity later on, that's what we mean. We want quality integrity, meaning that we want to minimize the degradation. And we need that so we can meet the bandwidth requirement. So we can, because if I lose that integrity, I'm going to have some uncertainty in the information that I'm trying to convey in that signal. Okay. All right. So bottom line, what we want to convey is that the signal behavior can be described in the time domain or frequency domain. Doesn't matter. And if we do it correctly, utilizing the correct mathematics, utilizing the Fourier transformation, we can convert that function into a series of trigonometric exponential type functions, and we could go between both domains. In some cases, it may be easier to operate in the time domain, which we'll see later on tonight. And sometimes it will be easier, and most often it's easier to work in the frequency domain. But that's what we shall see. Okay. All right. Any questions? Oh,
It's in the chat.
there's something in the chat.
Yes,
Okay. Let me open that up. Oop.
I can read.
Okay, please. Oh,
Why do we need this graph system in frequency domain?
why do we need to describe system frequency domain? Oh, because there will be instances where it'll be easier mathematically to describe the function in the frequency domain. When we get to really as the function of that signal becomes more complex, that means we're going to have to describe it using more trigonometric function, exponential, and it'll be easier for us to describe it utilizing working in the frequency domain. But it doesn't mean we can't work in the time domain. It's just often the mathematics just are easier. Okay. Yep. Okay. Okay. Oops. Why is it? Very, very strange. Port. Okay. Come on. everything closed up. Very, 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 very strange. Oh. Okay, basic elements. Oh. Okay, let's see if this works. Okay, let's find Zoom again. Okay. Share. Okay, basic elements of circuits part 2. All right, here we go. Let the fun begin. Okay, now I got a little notification for you. You will have to participate in this lecture. So first thing, you will need to be able to take a picture with your phone. Okay, is there anyone who will not be able to take a picture of the screen with their phone? If you can't, you can take a screenshot. That won't be the best approach, but it'll work. But again, I encourage you to take a picture with your cell phone when asked to do so. Okay, so now we're going to talk about circuits. Bottom line, circuit is that path that the signal travels, or electricity, data, whatever you want to call it, electrons, whatever. But again, it's this path that they would travel. Okay, and it can be different ones. So let's look at, say, power lines, high tension power lines. They travel miles at a frequency, a low frequency, okay? But high tension, high voltage, so they can travel long distances. When we talk about the integrated circuit, we have some lines going to be millimeters long. Those are long lines, but they're going to be operating in the gigahertz, high frequency. Okay, so the circuits, we can talk about macro scale, like power lines, and micro scale, when we start talking about signals on the package. So now we're going to look at some basic elements to our circuit. Now, we will take some of these very, very complicated circuits and try to generate equivalent circuits such that it describes what actually happens. So it gives us a model by which we can say, hey, if I'm going to use some of these very basic current elements to describe a very sophisticated event. Okay. Now, I can look at these elements and how they are viewed or function in the time domain and the frequency domain. So let's start looking. A resistor, okay? The resistor has this element of, I don't know what to call it, but it's just been, that's the symbol for a resistor for all my life. And by, in the time domain, voltage is just the current times the resistance. In the frequency domain, the voltage as a function of frequency is just the current as a function of frequency times R. So when I look at the resistor in DC, which is essentially one frequency or very low frequency, a resistor is the same. It functions the same whether I'm in high frequency mode or low frequency mode. Now let's continue on. Our inductor. Inductor known by these squiggly coils. The inductor is if I look at the voltage as a function of time, through an inductor, I have the inductance and I have the change in current. Okay, this change in current times the inductance will give me the voltage change as a function of time. I can also look in the frequency domain. Right? I still have my imaginary number, 2 pi, frequency L, I as a function of frequency. Again, do not worry about memorizing these equations. No, just be able to read them. Now, in the, okay, in the DC, the inductor will look like a short, okay? Just continue, just gives us a short. Okay. Now, at high frequency, the inductor can appear as an open. So depending on how we're operating will depend how these elements, especially inductor, will react. And then finally, we look at our capacitance. The capacitor, okay, will give us information about how the current changes as a function of voltage change. Okay. I can look at it in terms of the frequency domain or the time domain. At low frequency, it can look like an open, and at high frequency, it will look like a short, okay? At high frequency, the charging just so rapid, it just looks like a short, and that's okay. Now let's look at them in a little more detail. Especially the one that's going to be of interest to us is going to be this inductance and capacitance, because we're going to utilize those later on in the next two lectures. So let's get a better understanding of them or introduction to them for some. Okay, so let's look at this inductor. Okay, we said that the inductor, if I get my cursor over here. Okay, so the inductor, we're gonna, and for simplicity's sake tonight, we'll work in the time domain. So the voltage change, the voltage as a function of time is equal to the inductance times the change in current, where I is 0, the current is 0 at t equals 0, okay? So we're gonna change the current, and if we change the current in the inductor, it's gonna cause a voltage change. Now, so let's look a little closer. If I talk about the work or energy as a function of time. Hello? Okay, so we're going to look at, find my lost my cursor. Well, I thought cursor. Okay, there we go. Okay, so I'm going to look at the work, or is equivalent to the energy, okay, as a function of time. Now, okay, so work, energy stored as a function of time. We're going to go from 0 to whatever period that we're going to have this current change. Now, if I look at work, typically work is going to be V times I as a function of the derivative with respect to, and we're going to integrate with respect to time, okay? Because period is a time, okay? So VI. So now we are going to take this equation for voltage and substitute it in, okay, to our equation. And it's going to transform to this equation, a very simple equation. But now we're going to look at how the energy is stored as a function of current. So once we integrate this, we are going to be left with 1/2 Li squared. So the energy stored is going to be 1/2 Li squared. All right. Why is that important? So we're going to talk about inductance. It's a measure of the ability of the device to store energy in the form of moving charge. That's what we're going to have for tonight. So if the current is increased from 0 to some finite value and then decreased to 0 to the upper limit of the integration, okay, back to 0, the net energy input is 0. So that means we can charge up the inductor, but we can also discharge it. So we can charge it up and store energy, and we can also discharge it to remove the energy or to energize something else. Okay? So the inductance, to measure the ability of the device to store energy in the form of moving charge, current, which is moving charge. Okay? And so we are going to be able to charge up or store some energy in that inductor, and we're also going to be able to dissipate some energy in the inductor. All right, so here's your opportunity to participate. Again, take a picture of this screen because you're going to have to recall on it later on. So I'm going to give you a minute to take a picture of the screen. And if you do not have a camera, do a screenshot.
So Alfred, were you able to move the screen a little bit down? Oh, here we go.
Okay, are we good? Okay, so make sure you have this picture because we're going to call upon it in the next lectures. Okay. Now, okay, so let's talk about capacitance. Okay, we know the symbol.
Hello.
Okay, so again, the current as a function of time, as a function of capacitance, is the capacitance times the change in voltage as a function of time, where we're going to start with V equals 0 at T equals 0. So if we change the voltage, we're going to charge up the capacitor. Okay, and then we remove that voltage. That means we can dissipate the charge. So now let's look at the energy stored in the capacitor, okay, as a function of time. So we're going to look at it from time 0 to time t. All right. Now, okay, so now we're going to substitute I as a function of t into this equation for this I. Now I have VC dV with respect to time. This will now be from 0 to V, VC dV. And when I complete the integration, the amount of energy stored is 1/2 CV squared. All right. So we start off with our capacitor. We're looking at the current as a function of time. Okay. And at 0 time, we got 0 voltage. And now we're going to charge it up over some period. And it turns out that the energy stored or the work done is 1/2 CV squared. So if we look at capacitance, it's a measure of the ability of the device to store energy in separated charge. So we're going to charge up this capacitor and charge up the capacitor, and actually we're going to partition the charge. So I'm going to put negative charge on one side, separated by positive charge. So now I have created an electrostatic field from the positive to the negative side, but also I have this separation of charge that's stored. So I have this energy stored as separation of charge. I can dissipate that energy as well and charge back the capacitor. So now here's your second opportunity. Take a photograph of this guy because we're going to use it again in the subsequent lectures. So I want you to have it handy. And now this would be something that will be stuck in your mind when we get to the subsequent lectures. Okay? So I'll give you a moment to take that photograph. Okay. Okay, so now we're going to look at Kirchhoff's current and voltage laws, plural. Make sure we remember it, there's plural. Because, okay, we look at the current law. It says if we're at a node, okay, the total current entering the junction must equal the current leaving the junction. Okay. So the underlying law says that charge cannot accumulate at a point in a steady state circuit. Meaning, if I look at node A, there is no element there like a capacitor, inductor. It's just an equivalent node or where the current is coming in and current is leaving. Okay. So this mode where the sum entering equals the sum exiting must be equal to assure that there's conservation of electric charge. So sometimes Kirchhoff's current law is referred to as the conservation of charge. Okay, so there's no accumulation. So to make that true, okay, that means when we're at that node, and I got current 1 coming in, current 2, and current 3, I have to establish some algebraic reference. Now, you can do however you want. Some people, I will just I say current coming into a node is plus, current leaving is minus. That's not always true. You'll see some textbooks, especially I know my sophomore circuits book, the current Xing, like here, it said that things X leaving the node was positive, things entering is negative. As long as you have one mode of reference, just use it consistently, okay? Because you'll see with me, just happenstance, coming in is positive, leaving is negative. As long as you establish your own mode of operation. Okay, so with this, let's take a moment for inquiry. You have two situations where we're going to have current 1, 2, and 4 are given. You have to determine the value of current 3 that is leaving the node. So 1, 2, 4 entering the node, 3 is leaving the node. And you have two cases, case 1, and case 2. So in both cases, determine what I3 is. Okay. So I think we have a poll here. Let's see. We're going to take a. Oh, it's up there.
This one in poll.
Yes, ma'am.
I don't think we have this one in poll.
Okay, perfect. All right, thank you. All righty, so let's go to the answer. Oops. Okay, so if we look at case A, well, in all cases, I1 plus I2 plus I4 have to equal I3. What's coming in must equal what's leaving. 5 minus 3 plus 2 equals 4. So I3 is equal to 4 in the first case. And in the second case, I1 was 5, I2 was 3, I4 was 2. So 5 plus 3 plus 2 equals 10 amps. So in the case of B, the net charge coming into the node is 10 amps. So the net amperage leaving has to be 10 amps as well. Okay. Kirchhoff's law. Happens. Okay. Any question? All right. So now let's go to Kirchhoff's voltage law. So this is a conservation of energy. I mean, when we have a closed loop, okay, the energy gain must equal the energy loss. So if we cross a battery, we get increase in energy, participate across the battery. But if we go across a resistor or load, we're going to dissipate energy. And one of the things that makes this one a little more different from the current law is that you got to keep track of the polarity across the resistors. So relative to your source. So in this particular instance, you have here's our voltage source. We're going to drop across this resistor, but we can also gain if I look at these polarities because they're in the same mode as the source. Just means that current is going to be traveling in the opposite direction. But again, it's the conservation of energy. Okay? So the voltage gain must equal the voltage lost across circuit. All right, so let's take a little gander. Okay, so here we're going to moment for inquiry. In terms of current, resistance, voltage source, write a voltage law for the loop A, B, D, A, B, get over here, A, B, D, A. That's the first loop. The second loop is going to be B, C, D, B. Okay. So the second loop, B, C. Can you all see my cursor?
Yes.
Okay, great. Thank you. Okay, so B is going to be B, C, D, B. A is going to be A, B, D, A. And then secondly, we're going to write the current equation at node B, just in terms of the variable. All right, so let's take a few minutes to do that. Okay, so let's walk through this. A, okay? We're gonna have a voltage drop, so it'll be the current times the resistance, voltage drop. We'll come to B, and our voltage drop we're gonna take as negative, okay? We come across B, okay? We're gonna get a voltage drop. I got I3 coming across this 8 ohm resistor. Now I come to the voltage source that will energize the electron, give me a voltage plus 32. So A, B, D, A, I get a voltage drop of I times 2 ohms. So we're gonna make that negative. I'm gonna get a voltage drop of I3 times 8. Okay. And if I continue on, and then I go across my supply, energized by 32 volts. Okay, so I did not write it here, but we know that these units are, this was ohms, the 2 was ohms, 1 is amps, so these are in voltage. 8 ohms times amps, voltage, and the supply source is 32 volts. Okay? So I didn't take the volts on there, but we know that they exist. Okay, now I'm going to go B. Now I'm going opposite direction of my convention. So this is going to be positive, okay? All right. Oh man, why is this? Okay, why did that change? Okay, this beast should be 20, okay? This is not, what in the world happened? Oh, that should be 20 volts, okay? So now this equation will be okay, so again, plus 4 ohms. We're going against convention, that's minus 20. Okay. Now I'm getting a voltage drop here. Again, not going the opposite direction, so that's gonna be 8. All right, so now I have, this is my first equation. This is my second equation. And now you were asked to look at the node. So if we go to the node here, I got I1 coming in, I2 coming out, I3 leaving. So conservation of charge, I1 plus I2 equals I3. All right, so here we use Kirchhoff's voltage law to get us an equation as a function of I1, I3, I2, I3. And a third equation, which is a function of I1, I2, and I3. Okay. All right, so now, and what for us, I shouldn't say this is not for everything, but just for this evening, we are going to say, okay, the circuits that we are going to describe or utilize we're going to describe them utilizing resistors, inductors, capacitors, and power supplies. They're all really discrete components. We're just so that we can make these things called equivalent circuits. So we can describe the device, whether it's a voltage controller, whether it's a power supply. We're going to use these very discrete elements as well as Kirchhoff's current and voltage laws to describe them. And that's going to be our voltage regulator as well as our power supply network. Okay. Oops. So now you are going to enter into your breakout rooms. So there'll be 4 people in the breakout rooms. 2 of you all will focus on solving problem A. 2 of you all will focus on solving problem 3. We will have a poll, okay? So your job is to find the currents 1, 2, and 3 in the first circuit. Then the second circuit, you will find the currents 1, 2, and 3. All right, now let me give you a little refresher. Okay, so remember, resistors in series, I add them together. So in this case, they're in series. So the equivalent circuit here would be 20 ohms. Okay, because I've added those in series. They just add linearly. Okay.
Okay. So I'm going to put everyone in the breakout room.
Not just yet.
Hello.
I need to give them one more hint.
Okay.
Okay. Then when I have resistors in parallel, okay, when I have resistors in parallel, I have to add them in reciprocal. So 1 over R total is equal to 1 over R1 plus reciprocal of R2. All right, let me get a darker pen and do that again. So we're going to add them. When I have them in parallel, that's favorite color. Okay. So when I have them in parallel, 1 over the total resistance equals the sum of all the resistors added in their reciprocal. Okay, so that's the hint for that one. Okay, for B, the easiest, now look over here, you have 3 equations, 3 unknowns. Oh, doggone it. Oh, hate this. Well, you got the answer anyway. 3 equations, 3 unknown. However, you have to show your work on both of these equations and upload them. Okay, so you can send them to the breakout rooms, please.
Yeah.
A question, Professor.
Yes.
Yeah, the one at the right, for letter B,
Yes.
the 32 volts there is 20 volts, right?
Oh, thank you, thank you, thank you, thank you.
Yeah, thank you.
Thank you. All right. So off to the breakout rooms. And remember, you have to be able to upload your work for both of these problems.
Yes. You can
Questions inside Canvas. If you go to module and then module 1 and then group exercise, you'll be able to find these questions.
Hi, Nikki.
Yes.
Can we will we be allowed to use share screen within the breakout room?
In your own room,
Yeah, in our own room.
you should be able to. Not in the main room though.
No, in the breakout room. Yeah,
Yes.
thank you.
Yeah. No worries. Hello. Please find the group exercise in Canvas under the modules. If you go to day 1 exercise, day 1 group exercise, click, you'll be able to find those questions. And after you've done it, please upload it, take a picture of your solutions, and upload it back to Canvas. Thank you. Hello? For the participant who just joined us in the meeting room, we are doing a group exercise. I'm going to assign you to one of the group. Please make sure you be able to sign the Canvas. And then the exercise, you'll be able to find it in day 1, group exercise. Hi, Terry.
Yes.
Do you think we still have the time to cover everything that we plan to?
Um, I just got those 2 lectures. We might not be able to get to, well, I don't, let me look at the schedule.
Yeah, if we let them come back in 20 minutes from now, that will
Yeah.
be 7:25. I think we will be like 10 minutes behind the schedule. If the lecture that you are going to talk about the power supplies
Yep.
and the voltage, how much time do you think you need?
I could probably get them done in 30 minutes.
30, okay. With 30 minutes, then we should be close if we skip the break.
Uh,
Or we can, we just be late for 5 minutes. I think it's fine. I cannot see any tests. Hello, for 2 participants who just joined us. We are doing a small group activities, which we will need to use the Canvas. I'm going to assign you to one of the room to join them.
Hi, just Nikki, just to FYI, I
Yes.
have a terrible issue with the Zoom. I was at the beginning of the meeting, but when you tried out to do the breakout rooms,
Yes.
it kicked me out. I don't know why.
Really? Are you in a room now?
It says join. I'm gonna join. Bye.
Okay, bye. Hello, we have one participant didn't join the meeting. going to join in the small group. Okay. Terry, I'm going to join one of them for help.
Going where? Oh, you going into rooms?
Hello, for the participant who just joined us. We are doing a group exercise because they're almost finished, so I didn't assign you to the room. So just bear with us for a few minutes and the group will be back to the main room. Thank you.
Okay, Nikki. Oh,
Yes.
I'm looking at, it says, the break, come back from the breakout room.
Yes, we are a little bit delayed in what we planned.
How's that? I mean, because I'm looking at back to the main room at 7:20, 7:15. Okay, I see.
Yes, they will have you back in 25.
At 7:25.
Yes.
Okay. So if I look at this thing, so that says we're 5 minutes behind?
Let me double check.
Or
Section. We were 10 minutes behind.
okay,
They will be back in 25.
at 7:25.
Yes, instead of 15, 7:15.
Oh, okay, I see what you're saying. I see.
No worries.
Okay. Gotcha. Okay. Okay, 10 minutes behind.
This time is a 5-minute break, 5 minutes reminder.
Okay. Yeah.
For the two participants in the main room, we are doing a group exercise. They're almost back in the main room in a few minutes. Please use your own time to finish the assignment or exercise. You can find it in Canvas module, day 1, group exercise. Thank you.
Nikki, want to just go ahead and bring them in? Say 2 minutes, 3 minutes.
I will wait 1 more minute because we're counting down in a minute.
Okay.
I'm going to close the room. I'm going to close the room, everybody. We're counting down in a minute. If you're already finished, you can just quit the room. If you're not, you can stay until the countdown finish. Thank you.
Oh, I see. I see the countdown. Okay.
Yeah, you have a 1 minute countdown. Looks like we have some participants with issue with Canvas. They really accept it, but it won't roll. I think it's the Canvas with some countries. The internet is really bad. Hello. Welcome back to the main room. Professor Alfred, we're back.
Okay, so let's take our poll quickly.
Sure.
Thank you. All right.
Looks like the picture didn't show in my end. Is it showing your end?
What the poll?
Yes. With the questions.
Solve for each question. Yeah, I see it.
Okay, that's good. In my side, it won't show.
I think the one shown is for B.
Yes. Yes, it's for B. That's fine. Okay, we're gonna take 30 more seconds and then we will give the second poll.
Sounds good.
Answers.
Okay, 7 seconds. Or okay, I'll give you 10 seconds.
Times.
Okay. Share results. Okay, 70%. Okay, and let's have the other poll.
Sure.
I times 4.
Oh. Do you see it?
Yes, for this one, I'll be able to see the whole question.
I don't see it. Okay, let me try to hunt it down. It's not there. Looking around.
4 times 32. 28 minus 40.
What? Okay.
Were you able to see it?
No. Okay, maybe I'll come back here. Let me see. Pause recording, breakout rooms, whiteboard. I don't see poll.
That's fine. I can
Okay,
let me know when you want to end it. We have 1 minute and 20 seconds so far. 30
Okay.
seconds so far.
okay. I mean, how many participants do you have?
We have 67.
In
So 50% people have participated.
Okay, then I'll go ahead and close it.
Okay.
And
I can share the result. Were you able to see the result?
yes, okay. Okay, 87%. All right, beautiful.
Hey,
Okay. All right, so got 87% for the first problem and 70% for the second problem. That's very, very good. So we'll quickly go over those. Okay, we start off with this circuit. Now, since this guy, or these two are in parallel, we're just going to add them. So that gives us 20 over here.
You're not presenting.
Excuse me?
they can't see your screen.
Okay, let's go back. Oh, my error. Okay, can you see it now?
Yes.
Okay, so we start off with this circuit. These two resistors are in parallel, so we will add them. So the equivalent will be 20. Okay. So now we have these two that are in parallel. We add them in reciprocal. So we get the equivalent circuit of 6.7 ohms. And we have current 1 coming across. Now these two are in parallel. All right. All right. So these two in parallel. Okay. So since these two are in parallel, we're going to add them. Okay. And the current 1 and the voltage is 1 volt. So we're going to get 0.06 amps. Okay. Then at the node, we know what current 1 is. It has to equal current 2 plus current 3. And we know current 2 is going to be V2 divided by 10 ohms. And I3 will be V3 divided by 20 ohms. Okay. Then we use current law. Oh, I forgot. So these two are going to have the same voltage. So I2 equals 2 times I3. Use Kirchhoff's current law. This comes out to be I3 equals 0.02. We use the current law back at the node. I1 plus I2 equals I3 equals 0.4 amps. Okay. So with that being said, that solves that. I'll post these in Canvas as the solution in Canvas as well. And then the next problem, this guy. Okay, you got a couple of ways to doing this. Now, you can, all the young folks, I'm sure they know very well, they will just go online and get a simultaneous equation calculator. You can just put it in 10 seconds, the answer will pop out. Okay, that's fine. But some of us old timers like me, I only, I encourage you to do it by hand at least once. Okay. so you brush up on this because your students, when you decide to deploy this course, some of them may just come out of linear algebra and they just want to crank it out. So you can use the calculator to check, but we'll work it out. Okay, so I take this one equation for I3, substitute it in here, solve. Now I have two equations, two unknowns. Okay, now I'm going to solve one of those equations, okay, in terms of one variable. So I1 is equal to here. Now I'm going to substitute in for I1, okay, for this equation. And then I'm going to reduce it. And I'm going to get my first equation. Now I can substitute it back in to the equation and get my second variable. Then finally substitute back into the first equation and I get my third equation. Okay, so that's substitution. It's always good to do it by hand once. Okay, any questions? And obviously you all did very well, so I'm impressed. All right, so now we will just stop sharing and oh, shouldn't have done that. That's not good. Okay, now go to share. I can get the screen. Share screen 2. Okay, do you see introduction to power supply?
Yes.
All right, so now we're going to talk about a critical component to our package, supply, the power supply. Okay, so let's talk about power. Okay, have you ever wondered why when your air conditioner kicks on, you get the lights dim? Okay, it happens. And why is that? Well, when you get this large influx of current into your air conditioner, you're going to get what we refer to as voltage droop, because your power delivery is trying to deliver constant clean power. But when you make this, when this air conditioning demands a large flux of current, it's going to cause this droop in the voltage. And if the light bulb is in the circuitry, it's going to see this droop in voltage, hence your lights will dim. Okay. Well, in a similar manner, your power delivery network, which is your chip. Okay, there's your microprocessor. You got your power supply. Here's your power delivery network impedance. And when the microprocessor calls for power, in a similar manner, you're going to get a droop. Now, here, what actually happens is, it's sort of operating at 10 amps, but then it's going to demand some current from 10 amps to 50 amp. This is going to give you a very high change in current. And remember, we've seen this before, this delta I, delta T, okay? So here, what we have to do is trying to keep our microprocessor within 10% of the nominal operating voltage at all times. So yeah, when the microprocessor demands this large current, we can get the voltage drop as well, right? So just like our air conditioner, we want to deliver clean power. So we got to optimize it such that, again, for the microprocessor, when it makes this high demand, we want to keep it within 10% of the nominal voltage at all times. Again, just like our handy dandy air conditioner. And we don't want to see the voltage drop. And what's the rationale for the voltage drop? Well, what causes this voltage? Because we get this massive current draw. And what is the result, or what causes this current draw? It's going to require us to look at the complementary, let me go over here and make sure I get it, complementary metal oxide semiconductor inverter. An inverter is a very basic building block to our circuit. We get an input in, and the output is the opposite. So let's look at this case. If I got a high coming in to the inverter, the output is going to be low. If I got a low coming into the inverter, the output is going to be high. Okay. Basic building block. Now, one of the things we'll look at is that when I build my circuits, I'm going to build them out of this CMOS inverter. And turns out we can have 100 million inverters. We can actually have a billion of these things, okay? Because later on, we're going to see actually how do we make it. So let's look at the single inverter and try to determine the current draw on it. Now, we'll just jump a little forward. Now, remember, we talked about transistor action early on in level 1. Again, remember the transistor will have a gate. That's the equivalent to our faucet. That's going to control the current flow. We have a source, which is to supply the current, supply the charge. And we have a drain that's going to collect the charge. Okay? So that is our device. Okay, so with that being said, let's look at our inverter. So we have a metal oxide semiconductor field effect transistor, MOSFET. Metal oxide semiconductor field effect transistor. It's a complementary metal oxide semiconductor inverter. If we look here, we have our N-channel MOS capacitor, N-channel metal oxide semiconductor transistor. N-channel meaning I'm going to build it in a P-type substrate. My source and drains are going to be N-type. And for me to turn this device on, the gate has to go high. If I tie the source to ground and make the drain high, to turn it on, I have to make the gate high. Okay, so if I look carefully here, the transistors turn on when VG is high. Now, let's go to the P-channel device. Well, if I look at the P-channel device, inasmuch, you'll see that I have a P substrate, okay? Now, I'm also going to dope it such that I create an N well. Okay. So now this N well is a large region where it is N-type silicon. In that N well, I'm going to create P-type source and drains. Okay, P-type source and drain. Okay, in this type of transistor, the transistor is turned on when VG is low. Okay, you can notice, so when you have the little circle here on your gate, as opposed to no circle, that tells you this is a P-channel device, and P-channel devices turn on when the gate is low. All right, so now we have our N-channel and P-channel devices. So what we're going to do is we're going to take our P-channel device and our N-channel device. We're going to attach the input to the gates. Oops. Heavy finger. Okay, so our P-channel device is going to be up high, N-channel device low. The VDD or high is going to be attached to the P-channel device, and the drain is going to be on the N-channel device. We're going to attach the input to the gates of the P-channel device and the gate of the N-channel device. The output we're going to attach to the source of the two devices. Okay. So now if I look at the layout, here's the input attached to the two gates and the output to the drains. All right. So we got the layout. Again, P channel up top, N channel down low. And with that being said, now we're going to look at this thing of all these parasitic capacitors. We don't want them, but unfortunately, they exist. So in this schematic, you can see a variety of parasitic devices. We don't want them, but they're just part of the lay of the land. Okay. So now, here again, we got two pairs of cascaded. I mean, that means you have your P channel cascaded with your N channel, one here, one there. So now I look at a variety of capacitance. I got my gate to source capacitance, gate to drain capacitance, drain to body capacitance. If we have some wiring, that's going to have a little capacitant effect because the wire is going to be in contact with the dielectric. That's going to slow it, okay? So each time we toggle, or when the gates flip back and forth, what we will see is power consumed by the microprocessors. So they're going to charge, discharge, discharge. With that being said, turns out that all of these parasitic capacitors will charge 1/2 C V D D squared F. We saw that earlier when we were looking at the components. So the power, the energy stored. The energy stored is also the energy that gets dissipated. So unfortunately, with all these parasitic devices, we have this thing called dynamic power. That is the aggregate of all the parasitic capacitance times the VDD squared times the frequency. That's going to be the dynamic power. And that's what we're going to lose every time. Because if you call it, it's going to be 1/2. And then we're going to lose another 1/2 every time we toggle. So for one clock cycle, we will lose C times VDD squared times the frequency. Okay, that's dynamic power. So the dynamic capacitance is the aggregate of all the parasitic capacitance. So now let's look a little closer. So what is a power supply? If I look on a desktop, we got it plugged into the wall. So it takes that 120 AC, steps it down to 12 volts DC. Then our voltage regulator is going to step it down to 1 vote or whatever the microprocessor prefers, and try to keep that clean and keep it constant. Okay. And then it goes to the microprocessor for our desktop. For our laptop, okay, in that case, we have the adapter. Again, it goes from 120 volts AC, steps it down to 10 volts DC. The voltage regulator takes that 10 volts DC down to 1 volt DC, trying to keep it clean, and giving it to the laptop's microprocessor. We can also have the battery providing power or voltage to the voltage regulator. Again, they'll take that 10 DC from the battery, step it down to 1 DC to supply the microprocessor on the laptop. Now, and you know, when I say that, to say 1 volt DC for the laptop microprocessor, it's whatever the technology warrants. If your laptop, you know, is a 1 volt, beautiful. If the future, the goal is to get that voltage down to 0.8 volts, we want to get the voltage down. But whatever the microprocessor demands, that's what we provide. Okay. Now, if we look at the path from the voltage regulator to the die, there are instances where we can have 2 or more voltages needed by the device. So in this example, we're looking at 2 different voltages needed by the device. One we will refer to as VCC1, VCC2 will be the other, okay? Because your load here, your load here is demanding 1 voltage, and this load over here is demanding another. Okay, so how do we get there? Well, we're going to initially we're going to go to the motherboard where we're going to have our power planes, okay? And notice there will be, that's where we're going to get power as well as a ground plane. Okay, so we have our 2 power planes at the 2 different voltages, okay? And then the next level, we will have our socket power pins, okay? So this is how we're going to get the power and place ground on the pins, eventually to the package, okay? So this is going to go through this initial board. And then on the package, we'll also have some power planes that allow us for long distribution. Okay? Now, again, we have 2 different voltages that we have to supply. And then we have what we refer to as the die-metal grid. That's where we're going to actually have very narrow but thick line traces such that we can get power to the actual die or to the areas on the die that demand that specific power or excuse me, voltage, excuse me. And so that's why we refer to as grid, because they're going to have to, go up, down, laterally, so forth. But it will allow us to have large translation or transmission. Okay. And most importantly, get the correct voltage to that specific load. Okay. Whether it be the load voltage 1 to voltage 2. Bottom line is that we will utilize the voltage regulator to help us get the correct voltage across the motherboard, through the socket pin, through the package planes, eventually getting it to the metal grid, and eventually to our load. Okay. Now, let's take a moment for inquiry. That we're going to calculate the dynamic power. We're going to have 1 billion transistors. The fraction of transistors involved in that toggle at one time, we'll just say a fraction of 0.2. Okay, that just means that even though we have 1 billion transistors, for this particular function, we're only going to use a fraction of those. And then the average capacitance, parasitic capacitance, is 1 femtofarad. So that's 1 times 10 to the minus 15 farads. The voltage is 1 volt, and the frequency is a 3 gigahertz microprocessor. So take a minute to calculate the dynamic power. And don't worry about the units. You can work on those. Take some time out tonight or tomorrow, work on the units. But if you remember from the previous slide, the dynamic power is the aggregate of all the parasitic devices, V squared times the frequency. Now, in this particular example, we said that only a fraction of those billion transistors were involved in this particular toggle. Okay, we're going to calculate the total capacitance. Okay, that means we're going to sum of the all the parasitic capacitance. Now, it will vary depending on the technology. So again, for this example, we're just making it very simple that we will utilize the just very rudimentary case. We got a supply voltage, clock frequency. Okay, so the total parasitic capacitance is the number times the number of transistors times that capacitance. Okay, so we get 10 to the minus 6 farads. So then if I look at dynamic alpha is 20% of those billion transistors involved in this particular reaction. We got the total or aggregate capacitance, the voltage, 1 volt, frequency, 3.10 to the 9 seconds. It comes out to be 600 watts. So with just that one toggle on a state-of-the-art microprocessor, you generate 600 watts of dissipated power. So that's going to be manifested as heat. Wow. So now that tells you heat removal or thermal management is critical, extremely critical. If I'm just going to toggle only 20% of the billion capacitors, billion, excuse me, billion transistors on the package, I'm only going to toggle 20%, and it generates 600 watts just for that one transaction. So again, I cannot stress how important it is to remove the heat. Okay, so again, in closing, when we talk about the power delivery, the goal, deliver clean power, constant power. We got to worry about those things. We're going to try to avoid those ripples or those droops. Okay, it's important that not only do we operate, but we got to design it correctly. And finally, we talked about voltage regulator, the motherboard, the package element, how they are integrated to deliver the correct voltage to the correct device. All right, so with that, do we have any questions? Okay, stop sharing. Okay, get this out the way. Oops. Okay. Mhm. Okay. All right. The last lecture for tonight. Okay, we see the voltage regulator.
Yes.
Okay, great. Okay, so we're going to talk about a voltage regulator or regulator. Now, here's an example of a regulator. By definition, it's a device that manages or maintains a value in a machine. So here we have a gas regulator that we put on a tank, gas tank, and we're able to control the output pressure as well as monitor the pressure in the tank. So it allows us to regulate the actual flow. Okay? And that's our goal. Is again, a device that manages and maintains a range of values. So let's go to our microprocessor. And if we look carefully, we're back here. We have our voltage regulators in our desktop as well as the laptop. Okay. Okay, so again, we have a voltage regulator in our desktop. We're going to take that 12 DC from the power supply, step it down to 1 DC for our desktop component. The voltage regulator from our laptop is going to be 10C to 1 volts DC. Okay, so how do we operate, or how does actual voltage regulator operate? Okay, so the simplest approach is to use what we refer to as a single phase buck regulator. In this example, we're going to use power, metal oxide semiconductor field effect transistors as the switching components. We're going to have an inductor as the energy storage component. So remember that image we had on your phone, you know the relationship about the inductor and the current change and how it's related to the energy storage. Okay. Now, and we're going to have a shunt capacitor to help filter some of the high frequency noise. And if you recall, we had the system's impedance, and we will have the parasitic inductance and our capacitor. So we're going to try to minimize the impedance and minimize the noise or the ripple. Okay, so we got to look at how this works. Okay, so here's a switch. Oops, so here's a switch. The second switch that's in shunt. This guy can also be a diode. You'll see some examples where they have a diode here. Doesn't matter, you have a switch, diode, they will basically serve the same function. Okay, so we're going to be pedestrians and just sort of walk through this approach. Okay, and so here's my power supply in, and I'm interested, power supply in, and I'm interested in my power at my load, or the V out. Okay, so what's the first step? Okay, now we're going to start off with the switches open, and then, wait a minute, this did not go right. Okay, I'll just have to draw it in myself. Yeah, color. Okay, so first thing we're going to do is we're going to close this switch. Okay, and when I close that switch, okay, I'm going to, excuse me, I should do that on the next one. Oh. Okay, so I start off with the switches open. Now I am going to keep this switch give me a color here. Okay. Now, currently I have them open. And what we're going to do is we're going to close this switch. And when I do that, I'm going to energize the inductor as well as, well, we're going to start that first. Okay, so we're going to energize that inductor. That's the first thing we see. Okay. So now the inductor, remember when I'm closing, that DI, DT is going to go up, and go up and energize the inductor. I'm going to store energy. Okay. So now I'm going to open this switch. Okay. Now the energy is stored in the inductor. And but that inductor is in shunt with this capacitor. Okay. So now whenever I close this guy, when I close this guy, it's going to try to, that inductor is going to try to discharge and energize this capacitor. Okay. So again, I'm going to close the switch, energize the inductor because there's a change in current with respect to time. And you'll see the current in the inductor is going to increase because I'm energizing it. Okay. And that's for a given input current. Okay. Now, I'm going to look at this thing called duty ratio. That's the time on divided by the total time off. Okay. So I have some finite duty time because I'm going to be toggling back and forth. Now I'm going to open this guy. So that means the input is no longer tethered here. So that source is separated from the circuit. Now, when I do that, remember I've already energized my inductor. I close this switch. Well, as we saw earlier, once I remove the change in current or the driving the current, now I'm going to dissipate that inductor because now, look, I have a net circle. Oops. Now, once I close this switch, this inductor has a net circuit, complete circuit. The current, remember, the current law. So now you're going to drive this current down. The inductor is going to discharge. So we look at the inductor current, it's going to go down. So if I look at the reference or the output, the reference is going to be high. That's the output current, low. So it has a little bit of a ripple on it. And with that, it is the function of this capacitor to help us reduce this ripple. Okay. So again, we have our switch. We're going to close the switch. We're going to energize the inductor. Okay, inductor goes up. And then I'm going to open the switch and close this switch that's in shunt. Now I have a circuit. The inductor is going to discharge. So the current goes down. And that's on my duty cycle because I'm going to go on, off, on, off. So I'm going to have a little bit of ripple on my reference or the output voltage. Oof, why is my computer slow? And so here we get this current ripple in the inductor. The output ripple is small, but by utilizing the right capacitance, as we saw early on, that I can actually reduce this ripple. So it's very important when we talk about the metrics for the voltage regulator, how much power is dissipated? You know, because they got all those parasitic devices, but it's going to be important for this voltage regulator to deal with it and just try to deliver clean, constant voltage, okay? And then when we talk this thing about current density, how much of your area can be taken up by the voltage regulator? You want to try to keep the voltage regulator's footprint as small as possible because that means the other area can be utilized for components, okay? So we want to make it as small as possible, but we need it to be very, very efficient. And another metric is how well does it respond to these, how fast can your voltage regulator respond to low transient? Meaning, you know, when I turn it on the air conditioner, I want to try to avoid that voltage drop, okay? Again, that's the whole premise of this voltage regulator, to help deliver the clean power, and we take advantage of the capacitors and inductors, and we will see when, or we actually saw previously, we saw that depending on where we locate the capacitors, decoupling capacitors, they could be die side, land side, or remote on the board. Their capacitance level values can be high, can be low. Again, will depend on what type they are and where they're located. All right, so finally, so when we talk about the voltage regulator module, again, it's going to deliver the voltage output requested by the microprocessor. We could have multiple voltage requests, so we need multiple voltage regulators. The most common one will be the bulk regulator. Again, its quality will be based on how it responds and how it minimizes those ripples, voltage ripples on the output. So with that, I will close. Do we have any questions? Okay. Then I will ask Nikki, how do you want to proceed?
For example, the submission 10 minutes, we probably won't do it. Let them submit after the sections. What about, and they can still do the reading and discussion.
Okay, I lost you there. I'm having internet problems over here. So you're saying take a 5-minute break? Or I couldn't hear you, so I don't know what you said.
Sorry. No, I said we will still proceed to the breakout room for the journal article readings, but we will shorten the time. We will give in a total of 40 minutes for them to read and discuss, and then they will need to submit by their own.
Okay.
Yes. Okay. Thank you. And sorry, guys, today we're a little bit behind of the schedule. So now I'm going to send you to the breakout room, and then we will shorten the time for the activities. We do have one question in the chat. Professor Alfred, if you want to address why I'm doing that.
Okay, go ahead. I'm trying to.
Okay.
The performance of what's you take into account designing and circuits to ensure optimum regulation. Okay, yes. The root mean square of your power supply is important. I mean, what you get for what you pay. If you really want a high precision power supply, it's going to have a very small root mean square. I mean, that's just on the variation of the power coming out. Remember, because we said we want clean power. That clean would mean it's a constant voltage coming out. So again, you get for what you pay. Now, if you want a really clean, yes, you want a small root mean square. But if you have some flexibility in your design, you want to build in for that fluctuation. And it depends on, like I said, if you were talking about a voltage regulator, a 2.5 volt regulator for your door, for your car door, you don't need that type of precision, okay? But if you're talking about, a microprocessor, you want that as small as possible, and you're willing to pay for a quality voltage controller. And yes, and you definitely want to talk about the stability, thermal stability too. You remember there was this conversation about overclocking. Yeah, when you overclock, you can heat this thing up. And Your voltage regulators are typically built to operate within a certain temperature range. So if you take them outside that temperature range, they will not be optimized. There we go. Okay.
I almost assign you to the room.
Sorry, Nikki, for the interruption. Uh, I am alone in the session, in the breakout room.
Sorry, may I know your room number?
Uh, oh, I don't remember. I think it's 11.
11. Okay, let me double check. Right, that's true. hello, for sorry if I didn't pronounce your name correctly. We are doing a group discussion. I'm going to send you to a break room to join them. I'm almost. Hello, Santon. Thought you just joined the meeting. We are doing a group section for the readings. Still have 20 minutes, so I'm going to assign you to one of the groups. Hi, Hui. I saw you just joined the meeting. We are doing a group discussion activity, which will be finishing 16 minutes. However, I'm still going to assign you to one of the rooms.
All right. We're gonna bring them in.
Yes, they're already pulled.
Okay.
Yes, the breakout in a few seconds.
Okay.
Yes.
Well,
I think you,
okay, I see. I
yeah.
see. Yeah.
I think you can go ahead to share your insight when everybody's in the room. Here we go.
Okay. The two papers are a lot of information. Looking back now, it's almost worth it. It should have been worth it to actually come back and revisit both of these. Let me just highlight this front side power delivery versus backside power delivery. Yes, there are a lot of advantages with backside power delivery, but it will be a major technological advancement, but it's going to be high risk because just like going from 2D transistors to 3D transistors was a great deal of work in terms of research and development. Similarly here, you're going to have to be able to weigh the cost aspects of it. And there was another thing. If I recall, I think that's going to be a real big challenge. Again, it has the advantages, but it's going to take quite, I think, a lot of development. And you look at it, it's just so much that's involved. Where talking about from carrier wafers um, through silicon vias, and then that'll bring us to the other paper, which they talked about trying to get around some of this high power losses. So you're talking about 100 volts per centimeter square at high temperature. So you're losing that. That's the magnitude of the losses. And to keep up with this, they said they would have to redesign a lot of the insulating materials and interconnect materials. And one of the examples, they talked about silver. And I find that quite amazing. Excuse me, because in 1969, IBM tried to bring silver metallization up to par. Didn't work out. And back in the late 90s, I was one of the folks trying to bring silver metallization back on the scene. But at that time, there was such a large effort in copper metallization, whereas our group was looking at low K dielectrics and silver metallization. Well, here you look at this paper, they're talking about bringing silver back in heavy gauge wire bonding of copper clips with silver sintering. That is, makes me feel good that silver is coming on, potentially will come on scene. But let me ask this question. If someone can enter into the chat, what problems would you expect with silver metallization? From just your layperson experience. Yes, Abdullah.
Higher cost.
Okay, that's one, higher cost, yep. And interestingly enough, back in the early 2000s, silver dropped down to $29 an ounce, and they almost took it off the precious metals list. What's another problem would you expect with silver? What about your silverware?
Conductive.
Yes, silver is the best room temperature conductor known to man. Okay, the best room temperature electrical conductor by far. But silver, what happens to your silver fork?
Bendable.
Softer? Well, okay. Pure copper is soft too. But your forks, what will they tarnish? So yeah, that's one of the problems with silver. You have to be very, very, very careful not to have it exposed to any sulfur. So one of the problems in the fab, sometimes they use the etchants, and some of the gases will have sulfur in or utilize sulfur-based gases. In those cases, you do not want silver to be in contact. And yes, silver is soft. All pure metals are soft. So we put a little, you can put in the silver, you can put a little nickel, you can put a little copper in there to build up the strength by solid solution hardening. But I found that really incredible. One of the other things in this article, they were talking about this, when we talk about the design technology co-optimization. TSMC, that's sort of their thing where it says, okay, we're going to design everything together for improved performance and efficiency. And you start to think about it. In the old days, you had the people design front end processes to try to match up with the design, but the designs, excuse me, were already designed early on. But in this approach, you're going to try to design the processing and the circuit designs simultaneously to try to leapfrog the time from development to the lab, as well as try to address any integration issues early on. Because I remember my days at TI, sometimes when you do things separately, when it finally, you bring them, design them separately, processes as well as circuits, when you bring them together, they don't always match up. So I think that DTCO is going to be the way, it's just going to be the way you have to move forward in the future. Any comments from you all, any insights that you all found? Well, any questions about tonight? All right, so with that being said, I hope you have a wonderful evening or a great day for some. All right.
Thank you.
You're welcome.
Thank you,
Thank you.
Professor Paul, and thank you, Vicky.
Bye-bye.
Thank you, Professor.
All right, you're welcome.
Thank you, Professor.
Thank you.
Thank you so much.
Thank
Thank you,
you.
Professor.
Bye
Thank you, Doc.
bye.
Thank you, Lord.
You're welcome.
Thank you.
Thank you, Professor. Bye-bye.
Bye.
Bye-bye.